Okay, in this video, we use metrics or accuracy statistics to determine which is the better forecast. The book talks about three different ones. They talk about the mean absolute deviation, called MAD, the mean squared error, MSE, and the mean absolute percent error. And that's the one I want you to learn. I think it's the easiest to interpret. It's a little bit more complicated to develop, but not much. But it's much easier to interpret. I think it makes more sense to use it than the other two. They're all accuracy methods. You don't need to compare them, but you pick one, or you can actually use all three if you want. But just understand they're measuring different things, but they're all accuracy methods. We're going to use the Mape. So I'm going to go back to the worksheet where we did exponential smoothing. And exponential smoothing, if you remember what we did, is that we have a smoothing constant, and we used a weighted average where we took the smoothing constant multiplied by what just happened plus 1 minus the smoothing constant times our previous forecast. So this is what we did prior, and this is the forecast if alpha is equal to 0.1. I can change that number, and I can change this. Well, before we move too far, I'm not going to initialize at 0. You can see it gets good pretty quickly, but I'm going to give it some help, and I'm going to make the very first forecast equal to the first actual. And that way it doesn't have to work so hard early. Now that I've done this, how you calculate a forecast accuracy is that you've always have to have a forecast and what really happened. And when you have those, then you can calculate an error. So over here in the worksheet, this is what really happened. This is my forecast, so I can calculate an error. The error is just the forecast minus what really happened. But I'm going to calculate a mean absolute percent error. So sometimes this is going to be a positive number. It can be positive. You can see it's negative, but it can also be positive on somewhere else. So I always want to make the absolute value of that, so that these all become positive numbers. But that's just part of it. That's my numerator. That's the difference between what really happened and the forecast. But to calculate a percent error, we have to divide by what really happened. And then show that as a percent. And let's show a couple of decimals. So you can see that in the very first one, since I dummied up the first forecast, I probably shouldn't even include it. I don't think I will. But after that, you can see the next one. This is what really happened. This is what my forecast said, so I was off 16%. I'm off about 81 units, 81 houses sold. But that number can change from different product or different system. So a percent error to me makes more sense. I'm 16%, 17%, 14%, almost really good, less than 1%. So the trick is, what if I change this number? Oh, well, I need to do that all the way down. So I'm going to copy that all the way down to the very bottom, except the very last one, I don't want to calculate a percent error because I don't have an actual. This is the future, if you remember. This is the last one where I had what really happened in the forecast. So now that I've got all of these, I'm going to take the average of those, and I'm going to put that up here. And that's all this is a mean or average absolute percent error. If I take the average of all those, it says that with alpha equal to 0.2, my Mape, or mean absolute percent error, is 7.45%. So I could change this number. I can make it 0.3, and you can see it got better. I could go to 0.9, and it's better still. Is there something less than that? 0.8. Oh, 0.8, so I can't, it's not always the highest, but it looks like something around 0.8, maybe 0.7. 0.7 is even better. So what should alpha be And that's what we're trying to do, is that as long as we have what really happened and a forecast, I can calculate a Mape. Now we're going to use it to actually come up with the optimal smoothing constant. Because when I use the word optimal or optimize, that ought to be a key to you that, hey, I can use Excel's solver to do this. And you can. We're going to do a nonlinear optimization. And so I'm going to go under Data, Solver. And it's actually a really simple optimization problem. What I'm going to do is I'm going to minimize this, minimize my Mape, and I've only got one variable I'm changing, my smoothing constant, and then I'm going to add one constraint saying that my smoothing constant needs to be less than 1. You can't, it's got to be a number between 0 and 1. Because of the nature of this statistic, it's a nonlinear model, so don't go to this one, stay with nonlinear, leave that'll prevent the smoothing constant from being negative, and then hit solve. And there you go. Found a solution. So if you want to minimize, if you want to come up with, if you want to use exponential smoothing and you want to minimize your Mape, you should set your smoothing constant to 0.72. Thanks.